Okay, so maybe I'll give a kind of just a brief overview of where we are headed in the course, okay? And so we're going to start off, this week and the next couple of weeks, the next few weeks, on the topic of descriptive statistics, okay? And so descriptive statistics is kind of this broad category of describing our data. Okay, and it frequently involves using numeric summaries to summarize the data that we see. Okay. Once we've covered the topic of descriptive statistics, we'll move into the topic of probability. And so probability tells us how likely or unlikely certain events are. And once we get a handle on probability, we will talk about probability distributions. Okay. And so sometimes there are, situations or phenomena in real life that follow expected patterns, okay? So some real life phenomena or real life data follow certain patterns. Or we might call them distributions. Okay? And probability distributions will tell us how likely or unlikely certain values are. And once we get a handle on probability distributions, we can talk about sampling distributions. So probability distributions tell us how likely or unlikely certain values are. With sampling distributions, we get how likely or unlikely certain numeric summaries are. Okay? And so we will tie that, our understanding of descriptive statistics and our understanding of sampling distributions. So descriptive statistics tell us how to calculate numeric summaries, and sampling distributions will tell us how likely or unlikely certain numeric summaries are. We tie those together for statistical inference. Okay. And when we understand statistical inference, what we are doing is we are going to look at the numeric summary that we find in our descriptive statistics. We look at what the sampling distribution says about how likely or unlikely that statistic is, and based on that, by kind of comparing the numeric summary that we have, or the sample statistic that we have, compared to the distribution, we can make a conclusion about the population, okay? By combining our understanding sampling distributions. And the samples that we see, we can make conclusions about the population. Okay, and so I know a lot of this, what a sampling distribution is and all of those things, those might be unfamiliar terms at this point, but we will get into them, and I hope this will all make sense, because the idea that we are trying to accomplish in statistics is by just looking at a sample of data, we want to make conclusions about the population. So how can we do that? It's going to take an understanding of those samples and describing our samples with numeric summaries, and an understanding of sampling distributions, which depend on probability and probability distributions first. Okay, so let's talk about data and describing data, okay? So we'll talk about data. And so you can think about gathering information, okay, from our sample. So, we obtain a sample, and now we're going to gather information from our sample. Okay, and we want to summarize. We're going to gather information from our sample, or we want to organize this information. Okay, so you can imagine we've got a data table. And in our data table, we're going to have one row for each observational unit. Okay, so we're going to have and then we have one column for each variable. Okay, this form, this is what the book calls this stacked form. Okay, and so we can imagine gathering information on a random selection of people. So we can have name and their sex and their height, weight, maybe hair color. Okay, so this is like stuff on your driver's license, right? Okay, and so maybe we have Adam and Bill and Christine. Okay, so maybe Adam is male and Bill is male and Christine is female, and Adam is 6 feet and Bill is 5'9". Christine is 5'5". I don't know, 190 and 175 and 135. Hair color, we'll say blonde, brown, black, something like that, okay? And as far as the variables go, okay, there are two types of variables. Okay, we have numeric variables which tell us how much or how many. And we have categorical variables. And this tells us what type or what kind. Okay, and so looking at our data here, sex would be categorical, and height would be numeric, weight would be numeric, and hair color would be categorical. Okay. So far, so good? Yeah, all right. What if we had area code? We said, what is the area code? Is that numeric or is that categorical? Yeah, area code would be categorical. Okay, even though it's represented by a number, it doesn't tell us how much or how many. Okay. If your area code is 818 and someone else's area code is 310, it doesn't make sense to say, I have 508 more area code than you. Okay, that kind of comparison doesn't make sense. Whereas, if someone weighs 190 and another person weighs 175, it's fine to say this person weighs 15 pounds more than the other person. That's a totally fine comparison to make. Okay, if we ask how many siblings does someone have? What is that, numeric or categorical? Numeric, okay? Because it tells you can say you have two fewer siblings than this other person. That's totally fine to say. Yeah, hair color would be categorical. So area code, even though it's represented with a number, it's categorical, okay? It's mostly kind of like tied to a geographic location. And it will just tell you like what I guess what type in terms of the geographic location you were located in when you purchased your phone. Okay, the book talks about unstacked data. That's just kind of another form where I don't use as often, but you can just kind of look at the examples in the book about what that is, okay? Almost all data sets will have some kind of context, okay? Data often has context. And so all of those W questions you learned in grade school will come into play here. Your who, what, when, where, why, and how. These types of questions, these are often good questions to ask about the data, like why was the data collected or how was it collected? And that's often important as to giving the context in this study here, okay? We might want to summarize some of our data, okay? And so we'll just start off with summarizing categorical data with using what we call a frequency table, okay? Okay, so we can summarize categorical data, okay? And then, so we'll start with a frequency table. And so what a frequency table looks like is, again, this is for categorical data. You'll have the, you're going to list off each of the categories. So we could have something like sex, and then we'll talk about the frequency with which this particular category appears in our data table. So we'll say we have male, female, and then, you know, maybe other or did not state. Okay. All right, and so maybe you have 22 and 28 and 1 or something like that. So this tells us the frequency, you know, how many times. 22 basically means in our data, okay, 22 observational units. So in our case, an observational unit would be a person. So 22 people answered male. Okay. We can also have what we call a relative frequency. Which would just be the proportion. So we would add up 22 plus 28 plus 1, and we get a total of 51 people. And so the relative frequency would be 22 divided by 51. Okay, and I get, you know, 43.1%, so 0.431. And then 28 divided by 51, 0.549. And lastly, 1 divided by 51, 0.0196, so basically 0.02. Okay. And that would be a relative frequency table. So far, so good? Okay. We can also have a two-way table, okay? And so let's say I just copied this part. So this was a frequency table from the previous page, but we're going to create something called a two-way table. Okay, and with a two-way table, let's say we have gathered two categorical variables. Okay, so we gathered information on two categorical variables. Okay, and so far, let's say, you know, so one variable was sex, and then the other variable, maybe we're going to do hair color. Okay, and then so we'll create a two-way table that will look like this. So we have male, female, other. Okay, so this will be sex over here, and then we'll have hair color. So we'll say we have black hair, brown hair, blonde hair, we'll say red, and other. Other or did not answer, okay? And so all we know is that we have a total of 22 males, 28 females, and one person who responded other or did not respond for sex, okay? And then, you know, I don't know what we have for black hair, brown hair, blonde hair, red hair, or other, okay? And so, you know, let's say we have 7 and 8 and 5 and 1 and 1. Okay, and we'll go 10 and 7 and 10 and 1, and we'll do 1 here. Okay, so we have a total of 18, 15, 15, 2, and 1, and I think these things add up, okay? And so this is now a two-way table. Okay, and so basically this 7 says there are 7 people in the table, or people in our data, or in our sample, who are males with black hair. Okay, and that's all that means, is we've just gathered data on 2 categorical variables, and we can split that out, okay? And based on this, you don't have to copy this table, but I'm going to just put it on the next slide. Let me just get rid of this red line here. Okay, so let's say we did something like, I asked you a question, what percent of our sample is female? And you would answer me okay, well, what is the answer to this question? We would do 28 divided by 51. Okay, and I think we've already done this. We would do 28 divided by 51, and we get 0.549, so 54.9%, or we can round up to 55%. Okay. We can ask, what percentage of females have blonde hair? Okay, so that's saying what percentage of females have blonde hair, and we would answer this by doing what? 10 divided by 28, okay? And so we do 10 divided by 28, and we get 35.7%. Okay, now this is different from what percentage of blonde-haired people are female. Okay, so what percentage of blonde-haired people are female? Okay, so we look at how many blonde-haired people there are. There's 15 of them, and of those, 10 are 15. So 10 are female. So we'd do 10 divided by 15, and we would get 66.7%. Okay, so 10 divided by 15, would round off 66.7%. Okay, and I'm just assuming you guys are okay with going from decimals to percentages with no problem, right? Okay, we should be. Okay, and then lastly, let me just ask one more question, okay? And we'll say what percentage of our sample are females with blonde hair? Okay. And so, just want to give other students a chance to figure this out. So what would we answer here? 10 over 51. Okay, because here we're asking of our sample. So the key with all of these things is of females, of blonde-haired people, of our sample. This kind of defines what we're going to put in our denominator. And then the part where we say, what percentage of them have this or whatever, that kind of determines what we put in our numerator. So in all of these cases, we had 10 in the numerator, but the denominator differed from question to question. Yes, question?
So when you write our sample, it will be pretty much 100% of the sample. Doesn't mean any subcategory like female or male. So always need the whole sample.
Yeah, what percentage of our sample, or what percentage of our data, or what percentage of people in our data? Yeah.
So it's going to be the total.
Yeah, it's going to be the total, 51 people. Okay? Just want to make sure that all of these things are clear. Any questions on this stuff? So far, so good? Okay, great. Okay. All right, and okay, so before we get too far into talking about data and describing data and all of that, we might want to ask just how are we collecting our data in the first place, okay? Okay, and so we said, if we want our conclusions from our sample to work for the population, our samples need to be representative of the population. But as far as gathering data, this is a little bit tricky. So there's different types of data, okay, or different sources for data. Data. Okay, and then so one source would be anecdotal evidence. Okay, anecdotal evidence. This is kind of like stories, such as I knew someone who did this. And then this happened. Okay, so it's like I know someone who drank a bunch of milk and that made their illness go away, okay? Or, I know someone who, they sought this thing out, this strange treatment, and it cured them, okay? And I'm not discrediting any of these stories or saying that didn't happen. But as just from a statistical standpoint, there's not much we can do with anecdotal evidence, okay? Just because life is complicated, and so, this strange thing that happened, it could be because this odd treatment worked, or it could be just like anything else in life, something else could be responsible for what happened, and we don't know, right? It's like I wore my how I wore my Kobe jersey to the basketball game, and Kobe had a great game, you know, like he performed really well, right? So like that might be true, okay? We're not denying that that happened, okay? We're not going to say you're a liar, but we're just saying that might not be the reason why Kobe performed well that night, okay? And I'll miss Kobe, right? Okay. So, you know, stories, customer testimonials, these are all things, these are anecdotal evidence. Okay? But from a statistical standpoint, okay, we cannot use anecdotal evidence. All we can say is, well, that's pretty neat that that happened, okay? Just, and again, we're not trying to say like this isn't true. We're just saying like, well, that's neat, okay? That's all we can say, all right? So we, there are other sources, okay? We have observational studies, okay? And at least with an observational study, we can start getting at some actual associations, okay? And so with in an observational study, we observe our participants. We observe our participants, and we do our best not to interfere. With the, I'm going to call them subjects, but with the people we're observing. Okay. Ideally, we can gather information about any aspect that could be relevant to the outcome that we're interested in. Okay, so. The thing or outcome. Okay, so for example, let's say we're interested in things that might be related to someone's risk of type 2 diabetes. Okay, so we might want to know, you know, what factors play a role in type 2 diabetes. And so there's a whole bunch of things. And so ideally, if we're going to conduct an observational study, we can gather information about as many things about these people's life as possible. How many minutes of exercise are these people getting? How much sleep are these people getting? What exactly did they eat? What do their diets consist of? How much stress exists in their life? How much fun and recreation and leisure do these people are they getting, or things like that. But this is it's very difficult to gather all of this information. Probably things that we're most interested in would be the exact diet that these people are eating. But if anyone's tried to log calories or count calories for an extended period of time, it's a lot of work writing down exactly every single thing that you've eaten, okay? And so there's a balance between how much information can you collect and how much work is it to collect. this information, okay? But let's say you've gotten a bunch of information, okay? Then at the end of the study, you may find an association between a particular variable and the outcome. Okay? But even if you see an association, all you can say is that there is an association. You cannot say that one causes the other, okay? You cannot make a cause and effect conclusion. Okay, we have things called lurking variables, all right? Or confounding, I should say, yeah, confounding variables. Okay, there are confounding variables. These are, in an observational study, these are other variables that could be responsible for the cause, okay? Confounding variables, so other things that might be responsible for the cause.
Wait, I have a quick question.
Yes.
When you say responsible for the cause, do you mean responsible for like the outcome or
Yeah.
responsible?
Yeah, responsible for the outcome or responsible, there might be something else that's causing whatever we're seeing in the outcome, okay? So, you know, a lot of times you see some kind of study that says like, oh, patients, you know, some study was conducted and it was found that patients who had high levels of vitamin B were less prone to get sick or something, okay? That might be true, right? And I'm not denying that finding, but it doesn't necessarily mean that you should take a bunch of vitamin B and that's going to prevent you from getting sick or something like that, okay? It could be, there might be a study that says, I don't know, people who drink a lot of soda tend to die younger, okay? Now that could be an actual finding, right? And I think there was some kind of study that said like people who tend to drink a bunch of soda tend to die younger, okay? Well, does that mean soda is causing early death? Okay, maybe, maybe not. There's probably a better description of the finding could be something like people with healthy diets tend to live longer than people with unhealthy diets or something like that, okay? There's a lot of things that, you know, just because you find some kind of association doesn't necessarily mean that one causes the other, okay? Is that a question?
So are both the anecdotal evidence and the observational studies a correlation, not a causation?
So, okay, so anecdotal evidence, we can't really do anything from a statistical standpoint, okay? With observational studies, all we can say is that there as an association, okay? And you sometimes hear this phrase, correlation does not equal causation and things like that. But yeah, here in statistics, the word correlation takes on a specific meaning, so I'm gonna say association does not mean causation, okay? Okay, and so here's a silly example to kind of illustrate this point. You know, let's say you were an alien creature from another planet, okay, and you were observing a hospital, okay, and you don't know a whole lot about human culture or anything like that, And so you're, you're observing a hospital, and you notice that there is, that sometimes there's a man dressed in black robes, carrying a big book, and he'll sometimes enter a hospital room, and then he'll sit next to the patient and the man in black robes say something together, and then later that day the patient dies, or the next, very shortly after the patient dies. Okay, and you see this happen repeatedly, day after day, multiple times in a day. This man wearing black robes enters a room. Him and the patient say something together, or he says something, and then the patient dies shortly after. Okay. Now, if you were the alien reporting back to the mothership, you might say, "All right, we have to be careful about these people dressed in black robes because they seem to have the power over death, right? And they can cause people to die, right?" And that would be a silly conclusion, because we know that if you're Catholic or religious of any kind, a lot of religions have this observance of maybe like death rites or something like that, where when someone is very close to dying, they'll call in a pastor or a priest to say some prayers or things like that, and the person will die shortly after. Okay, and so it's not that the person dressed in black robes has power over death, but it's just that there is a confounding variable. There's something else, which would be the overall health of the patient that's in great decline, that is responsible both for the death of the patient and responsible for bringing about the priest. Okay, and so so it'd be silly to conclude that the priest's prayers are causing death, but a lot of times, and Facebook has just made this so much worse, is that people will share some kind of scientific study that says, don't do this because it's going to cause whatever health problems or something like that, and probably maybe an association was found. Okay, but you've got to think carefully. Is this really saying that one is causing the other, or is just that, if you think about it, there could be lots of other things related to the fact that we've observed this. Okay, so we've got observational studies, and then we also have experiments. Okay, and we can call these controlled experiments. Okay, and in controlled experiments, the researchers try to control as many aspects of variation as possible. Okay, and ideally they can make the conditions identical for all participants. Okay, and the difference is, except they make one aspect called the treatment different. Okay, different between the groups of participants. Okay, and so we might call one group the control group versus the treatment group. Okay, but again, everything else about these groups are identical, okay, in an ideal situation. All right, and so at the end of the study, or at the end of the experiment, okay, if we observe a difference between the control group and treatment group, okay, we can attribute that difference to the different treatments because everything else about them was held to be identical. We can attribute the difference to the different treatments. Okay, because everything else was made identical. Okay, so this would be, so in the ideal situation, we can get a bunch of people with similar genetic backgrounds, okay, because we don't want genetics to play in a factor, okay, so maybe we get a whole bunch of people of the same gender and similar genetic backgrounds. We try to give them all the same diet, we try to give them the all same daily schedule, we try to control as much as we possibly can, okay, and we just say this group gets a placebo, or basically something to keep them control group, and then this group gets the experimental drug, whatever it might be. Okay? And then if we observe a difference at the end of the experiment, we can say, well, everything about these people were identical or as close to identical as possible. So any difference we see between these groups is because this group got the treatment and this other group got the placebo. Okay? And so there are, aspects to help control things like placebos and blinding. These are just tools to help control the conditions, okay? And in this case, the condition that they're trying to control is we don't want the people to know which treatment they are getting. Want the participants which treatment they have. Okay, and but not all experiments are practically or ethically possible. Okay, and because of that, it's sometimes hard to prove certain things, right? So, for example, for a long time, people want to know, does smoking cigarettes cause cancer? And we know the answer to that is yes, but for a long time, the cigarette industry would argue, well, you haven't done an experiment, right? Because there's no ethical way to do an experiment on cigarette smoking, right? You can't say, well, thank you for volunteering for this study, and we flipped a coin and we've randomly assigned you to one of two groups. And so you 50 people, you are not allowed to touch any cigarettes, and we will check in on your lungs in 10 years. And you 50 people, thank you for volunteering. Starting tomorrow, you're going to smoke a pack of cigarettes every day for the next 10 years, and then we will check in on your lungs and see how you're doing, okay? I mean, that would be a fine experiment to see if smoking causes lung cancer, but it's not ethical to do something like that. And so for the longest time, all we could do were observational studies, and we would see, yes, people who smoke in general tend to have a higher risk of lung cancer, but then the tobacco industry would counter-argue and say, well, this was just an observational study. And yes, I agree that we are seeing an association between those who smoke and increased risks of lung cancer, but these people were genetically predisposed to lung cancer anyway, all right? And because of this genetic predisposition, that's what has actually caused them to start smoking, because there's something wrong with their lungs anyway, and that's causing a desire in them to start smoking or something like that, right? And, you know, it's hard to argue, and so, and we can say, you know, well, we did experiments with rats, and we forced these rats to smoke, and we saw them develop lung cancer. And then the argument was, well, those are rats and not humans, so doesn't necessarily work the same way in people, okay? And so, you know, it was kind of this back and forth. Finally, the tobacco industry agreed that smoking does cause lung cancer, but it's a much harder thing to prove some of these things because of practical and ethical constraints with the experiments. Okay. Is that all right with everybody? Okay. We're going to enter into a little bit of Chapter 2, and we're going to talk about displaying categorical data, okay? Now, the first part of Chapter 2 talks about displaying numeric data. We're going to actually just jump ahead a little bit. And so let me just kind of pull back this chart that we have, this two-way table, or not the two-way table, this frequency table that we had for categorical data on on gender here, okay? And so we can display categorical data with what we call the bar chart. Okay, and so the bar chart, on one axis you will have a number line that represents frequency, okay? Okay, and then on the other side you will have the categories. So we've got male and female and other, okay. And then, and we just draw the bar as high as the indicated on the number line, or the frequency, okay? So here, we'll draw this line for male, and I'm just kind of doing something like this for female, and then other would be something like that, okay? So this is our bar chart that we have here, okay? So just a few things stylistically. We leave gaps between our bars. And the arrangement of these bars is arbitrary. Okay, so we have, you know, if we wanted to put the female column first and then the male column, that's totally fine, okay? There's no reason why the bars need to appear in a certain order. If you want to put them in order of from greatest to least, also a perfectly valid arrangement. Any arrangement is perfectly fine. You can put them in alphabetical order if you have a bunch of categories. But if you think about it, there's really no rhyme or reason why the alphabet is in that particular order either. Okay, we learn the order when we're in grade school or younger, but that's it, right? Like, I don't know why E is the 5th letter of the alphabet. Okay, so anyway, we have this. Okay. We can talk about variation in a bar chart, okay? And so let's say we were just looking at let's say we looked at I don't know, flower colors, okay? Okay. And so we have red, pink, and white, okay? So you can have red flowers, pink flowers, and white flowers. And so let's say we went through and we counted up, we went to 2 different fields, and we counted how many red flowers, pink flowers, and white flowers we see, okay? Or maybe we went through 3 fields, just because we love this flower stuff. All right, and so this will be field 1. Field 1 had this many red flowers, this many pink flowers, and this many white flowers. Okay, field 2 had this many red flowers, this many pink flowers, and this many white flowers. Okay. Now, normally on a real bar chart, these would be kind of labeled. There would be some kind of number line. I guess that's no problem putting in a number line here. Okay, and then field 3, oops, had this many red flowers, this many pink flowers, and this many white flowers. Okay, and then so there's a question of which field shows the greatest variation in flower color. Now don't shout it out, okay? Variation, or we can even say diversity in flower color. Okay. So we got field 1, 2, and 3. Which one has the greatest variation? Oh, look at this. I can color these in. This is silly, but I'll do it. Where's my... shoot. That's not what I wanted to do. Never mind. I don't know where my brush tool is. Okay, well, never mind. Okay. So we've got this, and we're going to ask, okay, what do you guys think? Which flower shows the greatest variation in flower color? This is supposed to be flower color. Okay, and the answer is field 2 has the most variation. Most variation. Field 3 has the least variation. And field 1 is somewhere in between. Okay. Now why is that? Okay, now some of you might have looked at field 2 and said, oh, the red is 40 and pink is 40 and white is 40. That doesn't sound like variation. It sounds like they all have the same number, okay? But when we're talking about a categorical variable, that's actually what we want to see. Or, I mean, not what we want to see, but that's what it means to have lots of variation, okay? For a categorical variable, if the different categories are equally represented, that's the most amount of variation you can have, okay? Most variation when the different categories are equally represented. Because if you close your eyes and you picture what field 2 looks like, okay, you're going to see a bunch of red, a bunch of pink, and a bunch of white. Okay, that's going to be quite a mixture of flowers, okay? If you close your eyes and picture what field 3 looks like, it's going to look, by and large, very, very red, with a few pink and very few white flowers in there, okay? And so we would say field 3, there's not a whole lot of variation because everywhere you look, it's just red flowers, all right? Yeah, there's a few others, but we would say, you know, those are not very well represented, the other colored flowers, okay? And so when we're talking about variation for a categorical variable, it is better, or not better, there is more variation when the different categories are equally or nearly equally represented, okay? And there's less variation if one category appears to be very dominant in terms of its representation, okay? So that's what we're talking about when we say variation in categorical variables. Does that make sense? Okay. All right. As far as there's another way to display categorical variables, and that is with the pie chart. Okay. Now, in general, pie charts are not good. Okay. And that's because, you know, when you make a pie chart, it looks something like this, right? Okay. And then there's the question, you got red, pink, and white. And then you have to ask, well, which slice is the biggest? And it seems like maybe they're all the same, maybe they're not, okay? It's very difficult. Our eyes have a hard time identifying which angles are larger, okay? Our eyes have a hard time with angles. Okay, for whatever reason, we did not develop a good ability to distinguish between angles, okay? We are very good. There are certain things that we're really good at. One is seeing if things are balanced and level, right? Like when you're trying to hang up posters on the wall, you can spot one and be like, that looks a little crooked, okay? And you bring out the level, and it can just be off by a tiny bit, and your eyes can spot that, right? We're very good at identifying differences in heights, okay? Like I can just do things like this, and you can very easily see that, like, this one's the tallest, this one's a little bit the next tallest, and lastly, this one's the shortest one, okay? So when it comes to bar charts, our eyes are very good at distinguishing between different heights, okay? We can distinguish between heights and lengths. We can distinguish between heights and lengths very well. Angles, for whatever reason, we have a tough time with it, okay? Unless they're right angles, okay? With right angles, somehow we like those. Anything other than a right angle, it's like, which angle was bigger, right? It's hard for us to, we have a hard time with that, right? That angle versus this angle, like, who knows, right? Like, can we measure that? Maybe with a tool. How do I do this? I don't know. Never mind. Okay. All right. So this kind of stuff is harder for us. So that's why we don't like pie charts. Okay. We are going to we'll just call it a wrap here today. We'll finish a little bit early. Don't think this is the norm. We don't normally finish early. But today we'll end here. You guys have a quiz next week, so make sure you do your homework and try out the practice quiz. Be sure to arrive here on time, because if you arrive late, you're not going to get any extra time for the quiz. Okay, we'll see you guys next week.